Number 59, letter A. In what direction would the ship in exercise 3.57 have to travel in order to have a velocity straight north relative to the Earth, assuming its speed relative to the water remains 7.00 meters per second? Okay, so basically, so here's exercise 57, right? 2 problems ago. So what I have here on the left-hand side is a diagram of what it represents. Okay, so originally the ship was heading due north at 7 meters per second relative to the water. But now they want you to change that direction. Instead of the ship traveling due north relative to the water, the ship now will travel, take a look at the picture on the left-hand side, the ship will now have to travel at some angle relative to the x-axis, all right, and relative to the water, so that the resultant velocity is due north, right? So if we read the question carefully in this problem, I think part of the difficulty is understanding exactly what they're asking and trying to frame it in terms of a physics framework. So if I were to reread it slightly, it would say something like, in what direction would the ship in exercise 3.57 have to travel in order to have a resultant velocity? So I know the word's not in there, but if you read it carefully, that's basically what they're asking. Okay, so I know that this velocity that they're asking us for is going to be the resultant velocity, and that resultant velocity is straight north, and it's relative to the Earth, right? So in other words, the resultant velocity here is going to equal the velocity of the ship relative to the Earth. Okay, now, let's use this formula on the right-hand side, the relative velocity formula, to help me understand what I need to do in order to solve this. Okay, so this is what I'm looking for that I just circled. Okay, and what I'm going to do is I'm going to assume that that would be this in my formula. All right, because if I know these two pieces, I can simply sum them up to find this, because I know currently I have no idea what this is. So the velocity of the ship relative to the Earth should be equal to the velocity of the ship relative to the water, right? You might say, well, what's the B in the problem? Well, the only other thing in the problem is the water, right? There's a ship, Earth, and water. So that's the B, then plus the velocity of the Earth relative to the water. No, excuse me, sorry about that. The velocity of the water relative to the Earth. Okay, so this is what we got. All right, so now we realize that in order to find this velocity, okay, this resultant velocity, it's simply the summation of 2 component velocities, right? So once I know that, all right, I'm going to set up my component table. So I have my component table. Simply all this is just a table that shows the x and y components of all of the vectors. All right, so let me plug in here. So the velocity of the ship relative to the water. This will be the velocity of the water, right, relative to the Earth. And when I add those two together, according to my formula there, I should get the resultant vector, which in this case is the velocity of the ship relative to the Earth. All right, now, do we have these pieces? Well, take a look at the picture. We do, right? Here's the velocity of the ship relative to the water, right? It was 7.00 meters per second. They told us that in the problem directly, okay? They said if the speed, right here, if the speed relative to the water, meaning the ship's speed relative to the water, remains 7.0. So that's how I knew it was velocity of the ship relative to the water. Also, they told me that here's this we just have to read now in number 57. It says the local ocean current is 1.5 meters per second in a direction of 40 degrees north of east. So it doesn't say what that velocity is relative to, so therefore, since it doesn't mention it, we assume that it is relative to the Earth. So here now, I have the velocity of the water relative to the Earth is equal to 1.5 meters per second at an angle of 40 degrees north of east. Okay, so now, how does this help me? Well, let's first start breaking these things up into components, all right? It might not be clear yet how we're going to go about and solve it, but why don't we first break these vectors up, this vector and this vector up into its components, right? If you also notice, this vector right here in red, this is the resultant vector, right? This is the velocity of the ship relative to the Earth. We want the ship to be traveling due north relative to the Earth. That's what the question's asking. So, okay, just so we have everything in perspective. So now let's break down the velocity of the ship relative to the water. Okay, here I'm going to break it up into components. So here's the x component of that. All right, that's the, I'm just going to call this, this is going to get a little nuts here. Let me just call this Vx for now, okay? And then I was going to do V sub SW sub X, but that's going to be a little crazy. Too many letters all over the place. So now, and then let's do the Y here. All right, so this is the Vy. Recall and remember that this velocity in the x direction is negative because it is pointing in the negative x direction. All right, so let's go about solving this, okay? And you might say, well, how the heck are we going to do that? We don't know the theta. I know we don't know the theta, but just work with me here, all right? Let's just set up an equation. So I know the resultant, well, that's not the resultant. I know the hypotenuse, right? I don't know the angle, but I have it, you know, as terms of theta, and I'm looking for the side adjacent to that angle. Therefore, I'm going to be using cosine, right? So cosine is adjacent over hypotenuse. So the cosine of my unknown angle should be equal to the negative of the velocity in the x direction divided by 7.00. Okay, just moving things on over, then I would have the velocity in the x direction of this vector should be equal to the cosine. Let me write the 7 first. 7.00 cosine of theta, right? And that was negative there, okay? But just bring the negative sign on over, okay? So it should be negative. So now take that value, plug it into your table right away. So it's negative 7.00 there. I'm going to leave out the units. Now take a look at the y. All right, let's just do that. We probably don't even need to do that, but let's just do it anyway. So remember, I know the hypotenuse. I want to incorporate this angle, and this side, Vy, is opposite of that angle. Therefore, I'm going to use sine. So sine of theta is equal to opposite over hypotenuse. So the sine of my unknown angle should be equal to the velocity in the y direction, which is positive because it's pointing upwards in the positive y direction, divided by the hypotenuse of 7.00. So simply cross multiply here, and this becomes 7.00 sine of theta. Okay, just plug that guy in right away. So oh, I already made a mistake, I noticed. You're probably like, Andrew, what happened to the cosine here? Where did it go? You're right. I missed it. All right, no big deal. I'm always constantly checking, so everybody's prone to silly mistakes, but the difference will be how many times you check, you increase the probability that you'll catch them. And then that increases the probability of how the likelihood of you getting a better grade, let's say. It increases the probability of you getting an A, right? So, all right. So then let me plug in now this y value. This was 7.00 sine of theta. Cool. All right, let's get to work now on the this vector. Okay, the second vector, the velocity of the water with respect to the Earth. Let me break that up into components. So here, I'll do this one in red. Okay, so this will be my Vx, it's positive. And then here's my Vy. Cool, Vy. They're both positive. So first, let me work with my x. All right. So here I'm going to be using cosine, right? I know the hypotenuse, that's the 1.50. All right. I know this angle, I'm looking for the side adjacent to that angle, therefore I'm going to use cosine there. So cosine of theta is equal to adjacent over hypotenuse. Cosine of 40 will be equal to the velocity in the x direction there for the second vector times 1.50. And now simply just do your cross multiplication. So 1.5 times cosine of 40. So 1.15. 1.15. Great. Plug it in. So we have 1.15 here. All right. Now go to the y value. Okay. I know the hypotenuse again. I know this angle. I'm looking for the side opposite of that angle. Therefore, I'm going to use sine. So I have sine of theta is equal to opposite over hypotenuse. Sine of 40 will be equal to Vy over 1.50. Simply do your cross multiplication now. And we realize that the sine of 40 times 1.5 is 0.964. So 0.964. Okay, cool. Plug that in. 0.964. Okay, now let's add them up, right? Yeah, basically, but there's one little catch, okay? What do we know the resultant velocity to be? So focus on my picture over here, right here, guys. All right? focus right here. This arrow, right, that resultant vector, what direction is it in? Well, it's in the north direction, right? It's pointing straight up. So it has a y component, correct? Yeah, it's all y. But does it have any x component to it? No, right? They want us to travel straight north. Look back to the problem, I just circled it. They want us to travel straight north. Therefore, there is no x component. So guess what? Look at the component table now. Guess what this value is right here? What should the x component value of the resultant vector be? Well, we just mentioned it, right? It should be a big old fat 0. Okay, so let's just take that information and see what we can do now with it. Well, I'm not even going to worry about this side yet. I mean, I could, but let's just focus on the x part, okay? So remember, what did I say over here? I'm really saying that the velocity, all right, of the ship relative to the Earth in the x direction, right, should be equal to the velocity of the ship relative to the water in the x direction, plus the velocity of the water with respect to the Earth in the x direction. Okay, so what is this value? Well, 0. Okay, what's this value? Well, it's this, right? So take that and plug it in, negative 7.00 cosine of theta. And what's this value? Well, that was the 1.15. So put that in. So how do you solve it? Right. Add this term on over to the left, right? Oh, we might write 7.00 cosine of theta is equal to 1.15. Oh man, I see how to do it now, right? We got one unknown. Awesome. So solve it. Divide this side by 7. Divide this side by 7. Okay, I'm going to do the work here on the left now. So I have cosine of theta would be equal to 1.15 over 7, 0.164. So I got 0.164. And now just do the inverse cosine. Okay, so second cos of 0.164. 80.6. So there it is, ladies and gentlemen. Oh, that almost looked like a negative sign there. 80.6 degrees. That is the theta. That is the direction it asks, right in the question. This is the angle over here. So we found it. All right. Takes a little bit of creativity thinking about the different parts, but sometimes when you start piecing it all together, start setting up your component table and then thinking about, well, wait a minute, do I know what the x component of the resultant vector should be? It kind of starts coming together a little bit. All right. So we do know the angle. Okay, very good. And now it's asking us for letter B, what would its speed be relative to the Earth? So now they don't want to know the x or y component. They want to know the overall resultant speed. All right. So that means this guy right here. So that means I need to know both the x and the y components. So I already know the x, right? But what's the y now? Well, it almost seems like we have an unknown here, but remember, what did this theta represent? This theta, if you go back and look at all the math, that represented that angle, right? This theta was that angle. Okay, so I do know that angle, so therefore I do know this value. So I'm just going to write a little equals here, okay, 7.00 sine of now 80.6. So let me plug that in. So this is sine of 80.6. So do the math. So 7 times sine of 80.6. All right, so this becomes 6.91. So I'm just going to cross this out a little bit so not to get confused. So this becomes 6.91. Now add these two together. So 6.91 plus 0.964. All right, cool. So we get a y value of 7.87. All right, that's the y value. Now look, we can go through this formula now. I mean, right? But it's essentially, it's 0 squared plus then 7.87 squared. So what is it all going to work out to be? It's all going to work out to be just resultant velocity is going to be 7.87, right? Meters per second, right? It just has a y component. There is no x. So it's just the square root of something squared is itself, right? So that is all, ladies and gentlemen. So the resultant value or the speed, now remember, the resultant vector, right, was my velocity of the ship relative to the Earth. but overall, right? That's what I had said before. All right, so that would be the answer. So the speed of the ship relative to the Earth is 7.87 meters per second, and the ship must travel at an angle of 80.6 degrees. Now, I didn't even say location, right? I should have said 80.6 degrees north of west. Right? That's what that data represents. All right, guys, thanks for tuning in. I hope this helped. I know it was a long problem. There's a lot of parts to it, but if you definitely get this type of a problem, you shouldn't have an issue with any question that appears on your test. All right, thanks for tuning in. Please subscribe, tell all your friends about us, and I'll see you in the next lesson.